Okay, let's dive into this. Welcome to our latest explainer. Today, we're exploring a fascinating and honestly incredibly fun concept from the play-first programming philosophy. We are specifically looking at a project called the Python Chaos Equalizer. If you've ever felt totally bogged down by dry coding tutorials, or felt like programming is just this endless, intimidating wall of syntax you have to memorize, well, this approach is going to completely change how you think about learning to build software.
So think about this for a second. What if code wasn't something you just sat there and typed, but an actual instrument you played? Usually, when we learn to code, it's a lot of heavy textbooks, memorizing strict rules, and just staring at static text on a screen. But the play-first philosophy completely flips that on its head. It advocates for creating a live, interactive sandbox. You learn by touching, tweaking, and directly experiencing the results of your code right there in real time. It's really all about turning abstract theory into something you can actually feel.
Section 1. The Living Instrument, Moving Beyond Bouncing Spheres.
If you've tinkered with code before, you've probably done the whole make a basic shape bounce across the screen thing. It's a classic beginner step, right? But the Chaos Equalizer is designed to feel like real software right out of the gate. We're talking about building a Pygame window, 900 by 700 pixels with this really deep, dark background. Inside that window, you've got 100 glowing particles just drifting and orbiting around. But the absolute game changer here is a set of 4 interactive sliders sitting at the bottom. Particle speed, size, trail ghosting, and a chaos factor. You drag a slider, and those 100 particles respond instantly. No saving, no refreshing required. Now here's the catch. Pygame, the library we're using, doesn't actually have built-in sliders like a standard web page does. So we're going to need a little bit of help to build this instrument.
And that's exactly where an AI assistant comes in. Notice the prompt snippet here. We literally ask it to write the complete Python script and build those interactive sliders from scratch, making sure they respond to mouse clicks and drags. Now, we aren't using AI as some cheat code to skip learning. Not at all. Instead, think of the AI as your backstage crew. It's handling the tedious Pygame boilerplate and all that complex foundational math for the sliders so that you can step right onto the stage and focus entirely on playing, tweaking, and experimenting.
Let's see how fast we can actually build our sandbox. Once the AI generates the code, the assembly is lightning fast. Step 1. Copy the AI's code into a new file. Step 2. Save that file as equalizer.py right on your desktop. Step 3. Hit F5 to run. Boom! Just like that, you transition from looking at static text to interacting with a living instrument. You grab those sliders, you drag them around, and you watch the whole simulation react immediately.
Section 2. Twisting the knobs, breaking the limits.
So you have the instrument right in front of you. The real fun, and honestly the deep learning, starts when we stop using those sliders as intended and start messing with the underlying code that defines them. I challenge you here. Don't just accept the boundaries the AI gave you. Break them. What happens when we push the code past its limits? The AI wrote perfectly safe, functional code. It set a maximum speed that looks nice, behaves predictably, and keeps the particles looking like actual particles. But hey, we're in a sandbox. There are 0 strict rules here. Let's see what happens when we intentionally shatter those safe defaults and push the physics engine to the absolute extreme.
Now, what's really interesting about this slide is the sheer scale of the change we are making. Over on the left, we have the safe default code where the speed slider's maximum value, max_val, is set to 10. It gives you a nice, gentle drift. But on the right, we hack it. We crank max_val from 10 up to a whopping 500. We just gave the speed slider a massive multiplier jump. We save the file, hit F5 again, and crank that newly overpowered speed slider all the way to the right.
And the result is absolutely wild. The particles stop looking like individual particles entirely. Because you push the code so far past its intended visual limits, they transform into this crazy, vibrating field of light, right at the edge of human visual perception. It's such a tactile sensory thrill. You aren't just reading about variables in a textbook, you're feeling the dramatic impact of changing them on a totally visceral level. You are quite literally seeing the math break down and become art.
Section 3. Hacking the color engine, wiring systems together.
Okay, that was just a basic variable tweak. Now we're going to take 2 completely separate parts of our code, the physics determining the movement and the system determining the color, and wire them directly into each other to create something entirely new.
Originally, the AI gave us a static color assignment. The hue was just a set number running through the color sys module to give the particles a specific look. But we're going to replace that with the dynamic speed mapping you see on the right. We changed the code so that the hue variable is mathematically tied directly to the particle's current speed. We're telling the program, let the speed dictate the color.
The payoff for doing this is immediate, and it is stunning. Because of that one simple equation we just added, slow particles now glow a really cool blue, while the fast particles burn a bright neon red. You've just created a brilliant visual feedback loop. By directly linking the color engine to the physics engine, you've made a simulation where you can literally see the kinetic energy of the particles. You hit F5, slide the speed scale up and down, and you watch the visual temperature of the whole system shift in real time. It's so cool.
Section 4. The Accidental Architect. The Grand Reveal.
All right, let's slow things way down for a second and take a breath. Up until now, we've just been playing, right? We asked an AI for a sandbox, we broke the speed limits just to see what would happen, and we wired colors to the physics engine basically because we thought it would look awesome. But here is the prestige of our magic trick. Let me show you what you just accidentally learned while you were busy having fun. Without opening a single textbook, you just mastered event-driven programming. Seriously. When you were dragging those sliders and watching the particles react instantly, you were interacting directly with Pygame's event loop. You experienced firsthand how a program listens for events, like mouse clicks and drags, every single frame. The sliders worked through hit testing and state tracking, and you completely intuitively absorbed how that paradigm functions just by playing with the controls. Furthermore, remember when we hacked the colors to match the speed? Well, you practically taught yourself the color sys module. You learn that it takes human-friendly concepts like hue and brightness and seamlessly converts them into the strict red-green-blue format that Pygame actually requires to draw pixels on your screen. You manipulated complex color space conversions completely naturally without ever having to read a dry technical manual or memorize any documentation. And this brilliantly illustrates separating concerns. Your slider code, the complex math for the particle physics, and the instructions for drawing those pixels on the screen all lived in entirely separate functions within your file. Each piece of the code did exactly one job, and they communicated with each other through shared values. You weren't just writing messy scripts. You were actually engaging with real high-level software architecture.
Let's look at the complete play-first journey we took today. We started by transforming a completely passive animation into a living instrument. We leveraged an AI assistant, not to cheat, but to skip the boring boilerplate so we could get straight to the fun part. We deliberately hacked the physics limits and the color systems to get immediate, thrilling feedback. And in doing all of that, we achieved an accidental mastery of complex software architecture. The most advanced concepts were absorbed completely naturally, simply through the act of play.
Which leaves us with the ultimate question on our final slide today. What will you accidentally learn the next time you just sit down to play? The play-first philosophy completely proves that curiosity and experimentation are your most powerful learning tools by far. So, go open up your code editor, ask your AI for a sandbox, and start breaking things. Push the limits, wire systems together that definitely shouldn't belong together, and just see what happens. You're going to be amazed at what you discover. Thank you so much for joining me on this explainer, and happy hacking.